So I love recursion as much as the next person, and I find that recursion makes really complex data manipulation possible. But I don't always have the mental capacity to model the recursive algorithms in my head. And in such cases, I sometimes find it easier to switch from a recursive algorithm to a loop-based algorithm. And I just wanted to share how I do that. So to set up a context for this exploration, I have this collection of nodes, and the indentation here is just to make it easier to understand that this is a hierarchical set. But it's just a single flat collection such as that might come out of a relational database. And you can see here that each node has an ID, and it also has a parent ID that indicates which of the other relational nodes owns it in the hierarchy. Now what I want to do is take this collection of nodes and convert it into a tree structure. So to do that, in this demo, I'm going to use recursion. So I'm going to take that collection of nodes and I'm going to pass it into this generate tree. And generate tree is what's going to recurse over this flat structure and generate the tree. So if we jump down here and we look at this, the first thing it does is it takes the nodes and it groups them by parent ID so that I can then figure out quickly like how many, for example, nodes belong in the C2 node. Okay, so then once I have that index, I set up my recursive, sorry, I'm trying to get it all in the same thing here, my recursive function called traverse, and you'll see the traverse takes a parent ID, and what it's going to do is return a collection of all of the tree nodes that belong as direct descendants of this parent. So we're going to create this array of child nodes, which you'll see that I'm returning down below, and then essentially we're looking in that parent index for that parent ID. So again, we're trying to say, for example, find all of the nodes that exist under C2. I'm going to loop over those nodes, and then I'm going to append them to this child tree nodes. Now the recursive part comes in because this tree node here has its own children, and those children are defined as a recursive call back to this traverse method based on this nested ID. So instead of the parent ID, we're then getting the child node and creating its children based on the child node ID. So essentially, we continue to call this traverse method, or closure in this case, over and over and over again as we traverse down through the data structure, and then eventually this hits a bottom, right? So for example, we don't have any children that belong to a sub node of this tree, and at that point it just returns the data, and this traverse recursion starts to sort of roll back up, aggregating results, and eventually returning them. And then here you can see we kick off that traversion with the null parent ID, and then we just grab the first child because we know it only has one child. And if we jump over into the browser and we run this, what you can see is that that linear set of hierarchical nodes, hierarchical records, becomes now an actual tree structure, right? And we can see these IDs being echoed across the top: A1, B1, C1, D1, C2, D2, D3, D4, and so on and so forth. That matches the depth first walking of the tree nodes. Now, there's not a whole lot going on in this code, and people who are very comfortable with with recursion will look at this traverse method and it'll make complete sense. But what I find is that as the complexity of the logic around generating the data structures becomes more complicated, especially with things like special use cases, special handling of circular references, that understanding and modeling in your head this recursion can be complicated. So in such cases, again, I find it beneficial to switch over to a loop. And so the second version here uses the same exact data structure, but this time uses a loop instead of recursion. Now, ahead of time, this algorithm is definitely more verbose, but I think in some ways, at least for my brain, it's fundamentally more straightforward. So let's take a look at how this works. So again, we have this generate tree which takes our nodes. Again, we're indexing all the nodes by parent ID so that we can look them up. Now, here's where it gets completely different. Instead of making recursive calls, what we're going to do is keep a queue of nodes to explore, and we're going to push the root tree node onto that queue. And the root tree node here is just the record associated with the null parent ID, and we're just going to grab that first one, and we can grab its ID. So we can manually construct this root tree node, and then we can explicitly construct this queue. Now this explicit queue replaces the implicit call stack that's created by the recursive calls. Now what we're going to do is both consume and populate this queue using a single while loop. So what we're going to do with the while loop is continue looping while nodes to explore has data contained within it. And as long as there's data in this nodes to explore queue, which again, remember, starts with the root node, we're going to get the first item in the queue and delete it. Ideally, this would have been just like a shift method as you would have in JavaScript, but Cold Fusion doesn't have the concepts of popping and shifting the way JavaScript does. But essentially, this is shifting the first item off of that queue. Then, assuming that there are children that exist under this particular node, we're going to get all of those children, and then for each of those children, we're going to add them to the current child collection of the context node, right, of the while loop context node. And instead of, as with the recursive call, generating this children based on a recursive call, we're just going to leave the children empty for now. And then we're going to push that child, the one that we just created here, onto the nodes to explore queue, right? And that's the queue that we're consuming during the while loop. So the while loop is both consuming the nodes to explore queue, but then as it comes across new children, those new children are being pushed onto the end of the nodes to explore queue, which means that in subsequent iterations, we're then going to grab that item, and you're going to see we're going to flesh out the children of that item. So the main difference here is that with the recursive algorithm, the children are implicitly defined as the result of the recursive call, whereas in the loop-based algorithm, the children are left empty and then populated as part of subsequent calls or subsequent iterations of the while loop. So again, definitely more verbose, but in some ways, again, at least for my brain, fundamentally more simple, because none of the data here is being defined as the result of a call to another method. It's all kind of atomically understandable. And just to demonstrate, if we jump over into the browser and let's go to the other page, and this is the loop version, you can see that we have the same exact data structure. Right? If I tab back and forth, you can see that the data structure itself doesn't change. What you'll see though is that the list of IDs along the top does change. Right? And what we see is that the recursive call, which performs a depth-first iteration, if we look at the loop call, if we look at A1, B1, B2, B3, C1, C2, C3, C4, C5, C6, and so forth, what you've seen is this performs a breadth-first traversal or creation of the tree structure, meaning that it kind of goes across instead of down. That's neither good nor bad. I'm just pointing out that it is a different in implementation detail. Now, the nice thing, again, about this is that at any point, I can dump out the state of the world and understand what's going on. So for example, let's just say, let's just go right here and say like, if tree node.id equals, let's pick one that's like here, C6, right? What we want to do is dump out the tree node and dump out the nodes to explore and then abort. And now if we run this, what we can see is here's the current node and here are the nodes to explore. And you know what, we can also, let's dump out the root tree node. So we can see here's the state of the tree as it's being constructed. Here's the current node that we are looking at. And here are the list of nodes that we have yet to explore. Now, with the recursive algorithm, this becomes a lot more complicated because all of this data is actually spread across an implicit call stack. Unlike this, where all of the data is atomically kind of defined as part of the while loop. So, you know, to each your own, your mileage may vary. I'm certainly not arguing that all recursive algorithms should be replaced with loops. I'm not even sure that that's remotely possible. I love recursion just as much as the next person. But in certain cases, I find that a while loop without recursion is a little bit easier to understand, especially as the complexity of the data manipulation increases. I also think that it's a little bit easier on memory allocation because there is no call stack. There's just this flat iteration over data, and all of these any kind of intermediary data structures that are required as part of the data manipulation don't need to be maintained in memory. They can be dumped essentially at the end of the while loop iteration. But that's just a theory. I don't actually know that much about memory allocation, deallocation, call stacks, that kind of stuff. I'm not that well educated. But anyway, I find this helpful in certain circumstances, and I thought it might be worth sharing.